let's get started. Apologies for the delay. Yeah, so I'm very happy to announce Sarah Maglican, who is here today to talk to us. Sarah is assistant professor at the Informatics Institute at the University of Amsterdam, as well as a research scientist at the MIT IBM Watson AI Lab. Important to note. She got her PhD from University in 2017, working on logics for causal inference under uncertainty, and did postdocs in between at also IBM and working with Joris, right? Her current research focus is on causality-inspired machine learning. So that means applications to causal inference to machine learning, and particularly transfer learning and formally safe reinforcement learning. So someone giving guarantees. She wrote to me a lot of work that I will be mentioning is with Joris. So I think it will be a good introduction to some of the things the Mercury Lab might want to continue doing. So I'm very hopeful that this will be very nice for also in terms of content. And yeah, given that I have personal experience with Sarah going back about 10 years now, I think, when I think we first met in this project meeting. And I was immediately impressed with the amount of energy and enthusiasm that she brought, and ever since when I met her. So I think we are in for a treat. So I hope you will help me welcome Sarah. Sarah, take it away. Yours.
Thank you. I feel a bit bad because I don't know what you guys have been talking the whole day, and I'm also not sure where to look or position myself. So that's the camera. Okay, no problem. So I just want to you guys. Good. I know. Thank you. I'm fine. I fidget. So you know, I'm kind of an anxious person, so I fidget. So as Franz mentioned, I'm at the University of Amsterdam, but I'm also part-time at the MIT IBM Watson AI Lab. And I'm going to talk about causality-inspired machine learning, which is something I'll describe with this in a few slides. And in particular, we'll talk about the domain adaptation case, which is some work we did with Joris. So first, I'll talk in general about why causality, I think, personally is useful for machine learning, especially for distribution shifts. Then I'll talk about this domain adaptation work we did. And then I'll give a bit of a, just a sneak peek in some of the newer work we have been doing. And hopefully I will not take too much time. So first, I'll talk about this. Like this is, let's say, my point of view. Actually, yeah, sorry, I don't know if you guys can see. So let me know if I have to move if you cannot see the slides. The idea is that I'm going to argue that real-world machine learning, so real machine learning or real data, needs to deal with several things. For example, bias data, fairness, selection bias, as you saw, generalization issues with heterogeneous data, which are not AID. And it actually tries to find actionable insights, not just correlations, but causation. So all of these issues are covered at least, or are at least tackled in causal inference. So in causal inference, there are some tools on how to do systematic data fusion, how to reuse bias data, and in a sense, how to work on non-IID data. And causal inference is specifically a systematic way to extract actionable insights. So actionable insights, I mean, how do you decide how to do a policy? So not just, predicting what's happening, but deciding how to do interventions. So up to now, this is mainstream, especially after if you ever seen anything from Judea Pearl. Now I'm going to talk about something slightly less mainstream. So I'm going to argue that full causality, and in this I mean to find the unique causal graph. Sometimes it's too expensive or not necessary. For example, in some cases you do need to do a lot of experiments to fully identify the graph, because in general, from observational data, there are multiple graphs that fit the data, so you don't know which one is the true one. And so instead, I'm going to talk about this causality inspired, which is if you've ever been in US, you have things that are lemon infused, which do not contain lemon. So this is causality inspired. It doesn't necessarily need to contain causality, but it can use ideas from causality. It cannot pick and argue Joris. So Joris is kind of disagreeing, but it doesn't necessarily need to be identifiable to be able to actually provide insights that are useful for robustness and for distribution shifts. And specifically, as I mentioned, I'm just going to give an example here in the second part of the talk on domain adaptation. But I wanted to mention there is lots of related work. So other people have the other work, obviously, including in your research group. So I'm going to start with this kind of analogy between transfer learning and causal inference. So transfer learning is notoriously not very vaguely defined, talking about things that are vaguely defined. So I'm going to use this example, and I'm going to say that transfer learning is about predicting what happens when the distribution changes. For example, we have a self-driving car that is trained in US, and we want it also to work in UK, and people drive on a different side of the road. So this would be an example of transfer learning. How can we ensure that the self-driving car still works? And I'm going to argue that in causality, we're answering very similar questions. And one of the questions is, how can I predict what happens when the distribution changes, but in this case, after an intervention? And there are many works on perfect interventions. So Judea Per has developed the do calculus, and there are several works on this. In a perfect intervention, there are many definitions, but the simplest one is that you fix a variable to a value. And specifically, you want that the variable that you're intervening on, X, is independent of its parents. But in this talk, I'll talk about something else. I'll talk about soft interventions on a variable X. And in practice, this means that I'm going to change essentially the mechanism I'm computing X from its parents. And I'm also going to argue that this is very general. And since it's very general, it can model also things that are not interventions. For example, if you have data from one lab and data from another lab, the data from the second lab, they may be both observational, but you could consider that the difference is a soft intervention between them. So even if they're not, whatever this means, real interventions. And so I'm going to also argue that soft interventions and transfer learning, they have a connection. And this is not a new idea. And this is, I wanted to stress this. So this is a paper from SML 2012, in which several people, including Aziz, have discussed, so this is a famous paper on causal and anti-causal learning, and they are discussing, and here it's like the extract, that several things that people do in transfer learning, they could be seen as a causal problem or an anti-causal problem. And so this is from 2012, but since there have been several papers, and this is just a subset of them. So I'm saying many, many more, just to give you an idea. I did select them somehow in a way that it will be clear in a few slides. But all of these papers, I argue, and I think other people may argue too, is that they argue that causality allows us to reason systematically about distribution shifts. And this is maybe more for the booking.com people. I wanted to point out that this is not purely academic. So this is for Google Brain, this is from IBM, Microsoft Research, Amazon Services, Facebook, or Meta now. So this is like an interest that goes also into kind of industrial use cases. And so I selected the papers in a way that fits my personal bias towards graphs. So all of these papers, they do help us reason systematically about distribution shifts through graphs. And so you have all these kind of slightly different graphical representations. And so in the next few slides, I will try to describe at least how some of these representations you could interpret them and how they can help you to reason and kind of avoid certain common misconceptions that people do have about transfer learning. And causality allows us to reason systematically about distribution shifts through graphs, even if the graphs are unknown, which is several of these papers actually discuss the case in which the graphs are unknown. And in our paper, we also discussed even if you cannot reconstruct the macroinference class. So even if you have some missing data, essentially. So now I'm going to give you a description of the main allocation tasks. So I think the first two are quite standard definitions. And then the third one is one I will use through the talk, but other people might disagree. So I'll just give you my definition and then we can see what you guys think about it. So this is a task of supervised multi-source domain adaptation. So we have some source domains. For example, we have some data from some mice. We have some features. And we have a label, Y. And then we have multi-source means that we have potentially multiple sources. So you have data from just normal mice. You have data from mice which was an intervention was performed, for example, a gene knockout. So the distribution is different. And then you have some target domains. So you have some other mice in which a different knockout was performed. So the distribution has changed, but we don't know exactly how. And so in this case, we do have some data, some labels in the target domain. So that's called supervised multi-source domain adaptation. And what we're trying to do is we're trying to predict the labels in the cases we don't have. And so the task is to estimate the label Y from the features X1, X2, X3, X4, using the source domains and the labels we have in the target domains. So this is supervised. The unsupervised case is just we don't have any label in the target domain. So we cannot even see how if there is like, how the label has shifted in the target domain because we have all the labels are missing in the target domain. And so what we will try to focus on is in this talk will be actually this case of unsupervised multi-source domain adaptation, and we'll show how you can use the data from the target, from the sources, and some of the data from the target, essentially to try to see how you can predict this in a robust way. Okay, and then there is another task that I'm not going to talk much about, but I think a lot of people are interested in, and it's called domain generalization. And this is the most big task, and I think it's generally quite ill-defined. So in a way, I will use it during this talk, but people disagree. So I'll use it as this means that we don't have any data in the target domain. So we have some source domains for which we have labeled data. Then we don't have any data in the target domain, and we're trying to use the source data to transfer to this new unknown domain. We don't know anything about it. We don't even know how the features have shifted. Nothing. And I'm going to essentially assume that there's an underlying causal system. And in this case, in the new target domain, is it working? In the new target domain, there can be essentially any intervention on any of the features. And I'm going to kind of disallow that there's an intervention in Y, otherwise I think the problem is imposed. So this is a way to try to tackle this, the thing that I call domain generalization. So there is some work, as I mentioned. There is also like work from 2013 from Kun Zhang et al. On domain adaptation from a graphical perspective. And the idea, and here I'm just going to give you a little example. One of the ideas is that you can have, again, you have just normal mice, and then you have mice in which gene A was intervened. So each of these rows is a mouse, and each of these columns is a measurement. And we have these features X1 and X2, and we have a label Y. So now these are samples from two different distributions. So in order to kind of put them together, I'm going to do a very simple trick that probably people do anyway. I'm going to add a variable D. And this variable D will be, for example, 0 in the normal mice and 1 in the mice in which gene A was intervened on. And now I'm just going to pretend, since I added this variable D, I'm just going to pretend that all the samples come from a distribution in which we have the features XY, X, Y, and D. So I can represent this as a kind of pseudo single distribution, and then I can represent a causal graph on both the two distributions. And this D variable, the domain, is essentially encoding how the distribution of the features shifts across the different domains. So the domains here are, normal mice and mice in which gene perturbation was performed. If you have any question, by the way.
This is an intervention.
Yeah, it's in this case, there could be an intervention, but we don't know exactly what the intervention does. So there is a gene knockout. We know the distribution is different, but we don't know what happened. But this could easily be that they are just mice from different labs. So just normal mice, but they're from different labs. So maybe there is just the way these are measured, it may have a bias. From the formalism point of view, the fact that there is an action or not, it just doesn't matter because we're just talking about if the distribution changes or not, because we don't know how the action works.
Well, but so there's no unknown confounder pointing into P.
Yeah, that's true. So we do have some assumptions that there are no confounders between these variables, that I will explain a bit later, and indeed, that's true.
So then it counts.
Yeah, and also there is no causal. Generally, we assume there is no causal kind of connection between these variables and D either, so they cannot cause it. So let's assume we can represent this data with this graph. This graph can be also unknown. And up to now, you're like, okay, sure, I can do that, but why do I care? And what I'm going to argue right now, hopefully, is that even if we don't know the graph, we can still use things like separation and conditional dependencies, which maybe Philip had mentioned before, hopefully, to reason about invariances, or somebody else, actually, I don't know. So just to maybe convince you a bit further that this is, caution to put things together, because I know people sometimes are thinking either it's trivial or it's like just not okay to put different distributions together. This is an example I have with the structural puzzle model. So this is a set of equations. We have 3 sets of equations. And the only difference between each of them is that the equation for x2 is different. So here x2 is minus y plus some noise. Here x2 is 1. So this is like a perfect intervention x2, fixing it 1. And here x2 is 10 times y. And so you can represent these three structural causal models with a unique structural causal model, and we just have D as the domain as another variable. So this is the graph you get from the structural causal model. So you would take essentially, for each of the variables, you would take any of the variables on the right-hand side as the parents of the variable. So x1 doesn't have any parent. Y has x1 as a parent. So there is an edge between this. And in this case, x2 has y as a parent. So there's an edge between them. And x3 here has y as a parent. So there's an edge from y to x3. And then D is essentially just a switch that switches the way x2 is computed, because x2 changes across different environments. And I have a Jupyter notebook if you're fans, if you're very skeptical about it, I have a Jupyter notebook for that. Yeah.
Is it supposed to be a plus epsilon y in these two?
In plus epsilon here, yeah, this one is probably true. Yeah, this is a typo.
Okay.
But besides that, the typo, yes, there is a typo. Yeah, I will write it down later. Okay. So just to give you why we're talking about, we're putting distributions together, we're talking about it because, for example, we could have the first two structural causal models are our source domains, and the third one is our target domain. And again, why do we care about that? We care about that, and here it's again, I'm trying to plot it with some data. I want to show that if we have, so for each of these equations, I can simulate data. So these are some data for D0, these are some data for D1, these are some data for D2. They are simulated through those equations. And I can show that if I take, so this is y, and this is x1, and this is again y and x1, y and x1. So these are in different domains. I can show the distribution is very similar. So the scatter plots look almost identical. And this is essentially, I can say that the distribution of y given x1 is invariant across the domain. So it's the same in the domains, even empirically, I can say just from looking at the scatter plots. Okay. And now I'm going to try to see if y given x2 is invariant or not. So this is x2 and this is y. And so these different colors are the different domains. As you can see, so there are different lines. So the distributions of y given x2, they're fairly different, especially between the source domains and the target domain. But actually they're different in each of them. They're three different lines essentially. And so if I use the source domains and I try to fit a model, for example, just a linear regression, because I'm very lazy, I fit a linear regression line here, and then I try to use it to predict the data in the target domain, I'll have like arbitrary errors. And so here, in this specific case, I have a very big error of 30,000. And so essentially the distribution of y here given x2 is not the same in each of the domains. And so I can see this from the data, but essentially my point is that you can see it also from the graph if you know the separation, because it's a statement you can see from the graph. Specifically, P of y given x1, so y is here, x1 is here. P of y given x1 is invariant across domains is the same as saying that P of y given x1 when d equals 0, when d equals 1, it's the same as when d equals 1, and it's the same as P of y given x1 when d equals 2. So these are all the same. This is what I told you empirically. And so we can also just write P of y given x1. So we can remove d because it doesn't matter. And usually you remove d when you have that y is independent of d given x1. So this is how conditional dependencies help you to simplify conditional distributions. And so this independence here holds in this data empirically, but I can tell you, and this is, I'm not going to go into separation because I don't think I'm able to explain it very well, very quickly. But essentially, I can tell you that if you did know the graph, you could read that y is d-separated from d given x1 in this known graph, if you did know the graph. And this separation is, under some assumptions, a way to read conditional dependencies. So just to give you an idea, so here it's y. There is this path from y through x2 to d. This is the only path, and the path is closed because x2 is a collider. And if I condition on x1, which is here, x1 does not open any path. So I know that y is d-separated from d given x1. And if I know it's disseparated, I know it's also independent. And if I know it's independent, I know that the distribution is invariant. So essentially, things that are independent with the domain are things that are invariant with the domain. Parents? Yes. You know, if you have questions, let me know. Also at dinner if there is no time. Yeah.
No,
Okay. Good.
I just have a question.
Yeah. Good. And just to give you really hammer the point. It's always the same point. So P of y given x2 is not invariant precisely because we have y, which has this path through x2 to d. So when I condition on x2, essentially this path is open, so y is deconnected to d. And that's why, because we assume deconnections and conditional dependencies are one-to-one, that's why we know that, for example, x2 is not a good predictor. It will bias our prediction if you use x2 to try to predict y in different domains. And this is called also collider bias. So it's a well-known thing. And this is all assuming that we do know the graph. And then the task will be, if we do know the graph, the task is to find things that are separating. We call them separating features. So I'll explain in a few slides. So the separating features are features that have this property that disseparate y from d. So subset of features that disseparate y from d. This is what we're looking for. So this is, and the idea is that we want to look for this because then we know that the distribution of P of y, given these features S, is invariant across domains. That's what we care about. And just to give you an idea for domain generalization, so in the domain generalization case, I'm going to assume that essentially every feature can change. So there are edges everywhere. Does anybody have an idea which features now would disseparate D and Y? Not Yaris, but Philip can. So we have this. So it's a bit small. Sorry about that. But how do you disseparate this? And you know there are edges everywhere. From this other one here. This one from this one. Well, left. X1 indeed, and X1 is a parent. So, for example, if you use the parents, you can do that. And so that's why a lot of people, for example, invariant discrimination, etc., a lot of the people who attempt to do the generalization do look for the causal parents because they hope that then it can protect them against at least some things they haven't observed. So at least this is, I don't know if they do it consciously, but this is implicitly what they're trying to do. And so that's what I'm going to say, that generalization is like doing an intervention on every variable except y. I think this is one of the few well-defined ways to discuss generalization. Otherwise, it's very vague.
So only if there are no factors.
Indeed, yes. I have an example for that. Yes, indeed. So
And just one
yes.
Clarification. So if you say is invariant, you mean is invariant across domains?
yes, when I say is invariant, I meant the distribution is the same in the different domains. Yes, indeed. And so up to now, I just wanted to mention this again. I think people in causality knew it. At least Kuhn has known it for 10 years, but they haven't necessarily communicated it very well. We can argue whether I did, but this is something I wanted to maybe really point out if you haven't ever heard about it. And so, as Yaris mentioned, we're coming to that. One of the things that I think using graphs will allow you to see and thinking in terms of this separation is that, for example, something that is invariant in some source domains, it doesn't mean that it's going to be invariant in a target domain. So a lot of people are saying, oh, I'm going to train my computer vision method to be invariant to some certain data augmentations or certain different domains, and then it will work always. And then whatever I'm learning is going to be causal. And that's not necessarily true. So this is an example in which we have the domain here shifts the variable x1. This one is visible, right? Not like the others. Okay. But here x2, for example, is not shifted by the domain. And so we have, I wrote them as independencies, but we have two disseparation statements that you can read. So y is disseparated from d when I condition x1, because this path here is blocked. And adding also x2 doesn't really change. So you can have x1 or x1 and x2. So you could think, if you by chance find x1 and x2, that this means that x1 and x2 are both parents of y. And this is a bit one of the issues that people had when they were trying to use invariant discrimination. They were finding independencies, then said, it's independent across some domains. This means that it's causal And that's a misconception. So if you want that, it needs to be independent across, quote unquote, all domains or across all kind of possible interventions in a sense. So you need to be careful about that. Not just some domains, it has to be better formalized. And I think in the invariant risk minimization paper, they have like some theorem in which they showed under which types of environments they needed to have actual causality. Otherwise, it's just invariant. So something is invariant across some domains doesn't mean it's necessarily a causal. And here I'm really iterating this point because I was getting annoyed by people not getting it. But just to give you an idea, there are methods which do use invariances, and specifically invariant causal prediction from Peters et al., which do actually exploit this, but then you have to do something a bit more careful. And so this is a way to write invariant causal prediction is you want to have essentially the intersection of all of the sets that have this property. So you want to find the sets S such that they d-separate Y from D, but then you are going to take the intersection of the sets. And then those sets, you'll see that you'll find a subset of the parents of Y. And in this specific example, you have X1 that d-separates Y and D, and X1 and X2 that d-separates Y and D. So if you take the intersection, you get X1, which is the parent. And so there are some caveats. When is it parent or an ancestor? But let's assume no latent confounding for now. Then you can do this and you get the parents, or a subset of the parents. But because it's a subset of the parents, it's not all of the parents, sometimes it can be too conservative. So if you have this example here, and you have X1, this separates Y from Y, and X2, this separates Y, D from Y, and both of them also do that. You do the intersection of all of these sets, and the intersection is the empty set. And technically, the empty set is a subset of the parents because the empty set is a subset of everything, technically. So this is a bit, there are some caveats, but invariant features are not necessarily causal. You have to be careful, and there are people who have thought about it, how to do it in a correct way. So this is the summary. And this is more to the point of Yoris. If you do have latent confounding, so if you have like here, there is a hidden variable that causes both X2 and Y, then if you take X2, which is a causal parent of Y, this is not necessarily enough. It's not like, so D is not d-separated when you condition X2 from Y, because essentially there is, if you know the separation, there is a path here that gets open through the fact that X2 is a collider. But if you don't know, just trust me on that, and you can go and check the separation later. So essentially, you can use this separation to reason about things. And if there is latent confounding, you may want to use other things which are not necessarily causal parents. And if you want to do domain generalization and latent confounding, I think you probably need more assumptions because otherwise you cannot do it. And so the summary of these two common misconceptions is that if you use a graph, things that look complicated become very apparent, at least to me, because I reason in graphical models. And that causality, so using the parents, is neither necessary and not sufficient under latent confounding for transfer. So that's why I care more about conditional independencies than necessarily causality in this setting. So then, okay, so this concludes more or less the general idea. This separation is cool and you should use it for distribution shifts. And if you didn't get anything of this stuff, just go and look at the separation and try to use D as a domain in your graphs and see what happens, or maybe carefully see what happens. And this is more about the things we worked on with Yoris, like the specific example. And so I wrote this desiderata for a causality square domain adaptation method. It's a bit tricky because obviously it's written a posteriori given what our method actually does. So in the end, we have a lot of checkpoints, obviously, but just to give you an idea, I wanted essentially to have something that is able to find, so we want to be able to find dissipating features when the graph is unknown. And we also want to allow for latent confounders. And we want to somehow try to avoid parametric assumptions. So our method does not have a parametric assumptions, but they're in a sense baked in condition independence tests sometimes. So this is a bit with a caveat. We don't have parametric assumptions, but at the point. And this is, I think, what distinguishes it from other work. So we don't want to have just one domain variable. We want to have multiple context variables. And maybe Philip Wilker has already explained this. I'm not sure, but otherwise, in case, I will just give a short example. And having these different context variables, okay, allows us to distinguish between the target separately and a mixture of the sources. I think this is a very simple point, but I think it's like kind of crucial for our method and actually to improve transfer in multi-source domain adaptation cases. Yeah, okay. Yeah, it should be okay. Okay, so, and I want to also assume, I kind of avoid an assumption that if something is invariant across multiple source domains, then it's invariant also in the target domain, which is a bit of a subtle point, but we'll see when we talk about it. So we had some work in Europe 2018, and we had work was on unsupervised multi-source domain adaptation. So we had some normal mice, some mice with some gene modification on gene A, and then we had some mice in which another gene, gene B, was modified, and we wanted to predict the labels in that case. And so we're going to use multiple context variables, C1, C2, and etc. And specifically, we'll have C1 equals 1 represent the target domain. I'm going to explain how they're going to be used. And we're going to assume that the shift will represent it as a soft intervention. And we have some other assumptions that I will describe a bit later. So now the graph is unknown. Before we had the graph, if I had the graph, I can think about the separations and it works. If I do not have the graph, then we start having a bit more problems. So we're going to use this framework, joint causal inference, also from Joris, and we work with Joris on it and from Kassen. And then we're going to represent, so this joint causal inference framework essentially is the idea of, instead of having one domain variable, we're going to kind of split it in multiple context variables. So the paper is a bit more complicated than what I'm going to explain now, but just to trivialize the work, in a sense, what you can think about it is you have different distributions. We're going to add these context variables, C1, C2, and they will essentially be encoding the just indicators for the domain. So we can, in a sense, encode C1 equals 1 in domain 1, and C2 equals 1 in domain 2. And this one will call domain 0, just for simplicity. So, and you obviously this could be also, they have the same role as the domain variable we had before, but we're separating them because we want to specifically disentangle the target domain, as we will see. And now we're going to use these C variables. We're going to treat them as normal random variables. They aren't, so we're adding them, but we'll pretend they are. And then we can use methods that work on observational data with these variables. And we can even help these methods by adding them some background knowledge. For example, that the variables we added cannot be caused by the other variables. Or, and this is like an assumption that you mentioned, Franz, that there is no confounding between the system variables, so the normal variables, and these context variables that we added. There is no confounding between them. This is something you can add as an assumption into a causal inference method, and it will work. And you can, it's a framework that you can use with multiple methods. And if there is no missing data, we get something like a Markov coincidence class. So we get a set of different graphs. But the problem is, in our case, we do have missing data. So I'm going to talk about the separating features, which, as I mentioned, are sets of features that separate Y from the context variable C1. And this is essentially what we're going to try to find when you don't know the graph. And now we don't know the graph, then we could think maybe you can just test these conditional dependencies, because in the end we care about conditional dependencies in the data. So can I check if X1, this is conditionally dependent of Y given C1, so this separates in a sense Y and C1. And the problem is I never have Y when C1 is on. So I have like missing data, not just at random, I have consistently missing data in our target domain because we're doing unsupervised domain adaptation. So we cannot just test it in the data. And one solution that other people have thought about, so this is Rojas, Carulla, and others, it's called invariant models for causal transfer learning. One possibility is that if you have different source domains, you're going to try to see which features, for example, X1, this separates from Y from the domain in the source domains. And if it works in the source domains, I'm just going to assume it implies it will also work in the target domain. And this is in general not true. So I have an example here that I think we probably don't have time to go specifically now, but we can talk about them in the discussion. In the plots I have in this example, the green plots are the things that are the distributions in the source domains. And you can see that for both X1 here and X2 here, these distributions look the same. But when I add the target domain data, which are these blue ones, for X1, the distribution still looks the same. And for X2, the distribution is very different. And so you have cases in which you think, so things that do not change in the source domain may still change in the target domain. So you have to be careful about it. And essentially our method is able to also use the data from the target domain. So this method here kind of throws away the data from the target domain conceptually. Instead, we're going to use both the data from the source domains, but also this data from the target domain. So the idea in the end was that we used a lot of conditional dependence tests, and we tried essentially with the theorem prover to see if they imply the one that we wanted. We have some very technical assumptions that maybe are a bit too technical for now, but again, we can discuss. One important one is that Y cannot have an arrow pointing into it from at least the target context domain, and in general from the domain. We have some assumptions on how you can transfer some conditional dependencies from one domain to the others. Here I have an example that we won't go through. So we actually did an example. We proved it by hand in the paper. But in practice, you don't want to, for every conditional dependence test, prove for every graph which are the features that will work. So instead of doing that, we use a theorem prover. That is the thing that I was really into. And so what we had a theory. We have the assumptions that are technical, but we can discuss later. We had all the conditional dependence tests we could do on the data, including the ones which had these C2s, so the context variables. And then we used a logic encoding from Keating and et al. Of this separation. So this allows us to reason about this separation. And when I say reason, I mean properly reason through a theorem prover. So this is answer set programming. So you can prove things. And the theorem prover is just bingo if you're interested in it. Anyway, given a set, we could show that something is provably separating, which means we can guarantee that the distribution of Y, so the distribution of Y given X1 does not change in the target domain. So we can prove it. We can prove this does change, or in some cases we couldn't know if it changes or not because there were multiple causal graphs that fitted these other conditional dependencies, so we weren't sure whether X1 would be satisfying the separating feature set. So if the separation that we're looking for would hold in the true causal graph. So I think we're almost there. Yeah, exactly. So I'm going to speed up a bit. So I mean, it's almost there. We're good. Yes, we're good. Okay, so essentially we have this magic box that if you ask me for a feature X1, given a set of conditional dependencies, you ask whether X1, Y given X1 is invariant across domains in the target domain or not, even if there is no Y in the target domain. So under some assumptions, we can prove it's always invariant. In some assumptions, we can prove it's never invariant, and in some assumptions, we can be agnostic because we don't know. So we say, I don't know. So these are the three cases. So given this magic box that tells us which features are safe, we essentially kind of combine this with a feature selection algorithm in the paper, and the feature selection algorithm was random forest. So we choose sets of features through random forest which have the lowest source domain loss. And I wanted to point out that the features also included these extra variables that we added, these context variables. And then essentially the idea was just take greedily the best set of features in the source domain and see if it's provably separating or not, and then just iterate until you find one. And the idea of this would be that at some point you find a set. So you try the first one, it didn't work. You try the second one, it didn't work. The second one here worked. So if you do find something that you can prove is safe, then you can use this set of features, learn on your source domain data, and then you have some kind of bounded generalization error in the target domain. And so this is essentially what we wanted. And now, maybe to kind of summarize a bit, the desiderata I talked about in the beginning, some of them like being able to represent changes with an unknown causal graph, allowing for confounders, avoiding parametric assumptions, and being able to distinguish the source domain from the different, so the target domain from the different source domains. This is all we could do through using essentially joint causal inference. And then additionally, we also could do these other two tasks, which were trying to essentially use also data from the target, so unlabeled data from the target, in order to avoid the assumption that things that work in the source domains that are invariant in the source domains would also be invariant in the target without looking. So we're actually going to look at the data in the target. And specifically, we only care about things that work in the current test domain. So we look at the test domain and we find things that work in the current test domain. We're not trying to find things that would protect us against everything. So we don't have a self-driving car that is trying to work anywhere on any planet in the solar system. We have a self-driving car that is trained in US, and then we have a label data in UK, and then we try to see how it would work in UK. It doesn't necessarily need to work in other places as well. It's a kind of a very specific task. And we don't need to find the causal graph or neither the equivalence class, which is what people usually do in causal discovery. And that's why I'm saying it's causality inspired. We have a lot of limitations. Otherwise, we would be done. We can go home. We have to solve causal domain limitation. So some of the limitations is that we have these three cases. You can prove it's separating, you can prove it's not separating, or you're unknown. And sometimes maybe really having something that is you can prove it's separating, similarly to formal safe reinforcement learning. Sometimes it may be a bit too strict, so too conservative. So you may throw away some of the features which are perfectly good and predictive, just because you think they might not be actually safe in the target domain, so that they will shift and bias your prediction. And so there are some ideas on how to improve on that. And one of the big problems, not just of this work, but also of the logic-based encodings, is that they're not very scalable. And so they work in the order of tens of variables. And so this is one big issue that I'm planning to work on. How to essentially try to do this approximately, or how to try to scale it up. But it's a very difficult problem, so it's kind of going to be difficult. And we do have some work. So I wanted to apply this multitask reinforcement learning, for example, factor this. In the end, I didn't, but just because I was working with Wei Huang. And so instead of using our method, we use a related method called CD0. And in this case, instead of having context variables, you have these thetas. And there are some slight differences, but the general framework I showed in the first part of the talk still holds. So you have a graph, and these thetas encode the changes. And so we wanted to use this method essentially to do multitask reinforcement learning. And so, yeah, very quickly, I'm going to discuss this. So we call it ADRL, and this is a paper in ICAI. And so we had different source domains. So you can play Pong normally. You can rotate Pong and play it. You can play Pong with noise. And the idea is that from these source domains, we estimated a model which looks like a dynamic Bayesian network, although these are like latent. And so you only observed the images, the actions, and the reward. And this part, the part of the state and the graph, are invariant. And instead, the only thing that changes across the domains are some low-dimensional parameters. And so we have a simplifying assumption that there are no new edges in the target domain. So the graph, this stays always the same. The only thing that changes, also the edges stay all the same. The only thing that changes is the values of the parameters. And so we use this to learn a policy across different source domains that is parameterized in these thetas. So then when we're a new target domain, and we have a new type of rotation, so it's still a rotation but with a different angle, then we can quickly estimate the angle, and we can just plug in our policy, and then we can show it without fastly. And that this factor representation, so having the graph here instead of having everything fully connected, actually helps us to be more efficient. So the conclusions, by the end of time, I guess, but this separation is, cool. You should know the separation if you don't know it. And it allows us also to reason about invariances and distribution shifts, which I think maybe was not the original plan, but it does. Again, not a new observation. And maybe a slightly newer observation. This is true also when you don't know the graph, which maybe people still knew, but also when you have missing data. And the disseparation logic encodings allow us to reason, like, they're very flexible and allow us to reason a lot about these things, but they have some issues with scalability. So these are like the conclusions.
Thank you, Sarah. And more questions, maybe from here, from the audience, Philip?
Yeah, so how you infer whether this one particular condition holds through these other conditions? Is that true?
So we have a transfer assumption for some subset of assumptions.
Yeah.
I can show you the slide.
So
is this what you're asking, or are you asking in general? Because the other ones we test.
Electricity or improver. This is combining the condition with tennis.
Yes. methods I think are more general, but this is a question that Phil David, for example, has asked one of our talks.
Mhm.
I think he asked you, but yeah, still.
But then, okay, yeah, so the answer is it's slightly different.
Just the encoding is different, but if you were to encode the graphoid axioms in answers to programming, you could use that as well.
Yeah.
Just this one has more inductive bias.
So it encodes the separation axioms in images.
Yes.
Restricted.
Exactly.
Yeah.
But you could do that in theory. It's a theorem prover. You can do a lot of things.
I also have a question.
Yeah.
So just a bit more like at an intuitive level.
Yes.
So you are trying with these features C1, C2. So these are now kind of like features of the domain in some way.
Yeah.
And in order to try and do more generalization rather than treating the domain as a index.
Yes.
You're now looking at its structure.
Yeah.
And you're to some extent, but without actually doing that, that means somehow you're trying to learn about the true Bayesian network in some sense here, right?
Wait, so yeah, I was being a bit, so I think maybe I was a bit unclear. Like we do use still the bias that there might be an underlying causal graph, and that's why the separation actually allows us to infer another separation which was missing. So there is still an idea that there's a causal graph, but we don't know it. Does this mean that?
Yeah, but and because to some the data is also it's observational data in the end, right? You're not taking any interventions. You are putting some assumptions as indeed the C1 and C2 are not themselves influenced, and that helps. But to some extent, it still feels like you're constructing now the Bayesian network from this observational data. So yeah, but you're saying you're not doing that. So what am I missing? Like intuitively, why is the task different?
Oh, it's just because they're like you can consider it as observational data. You just have in a sense multiple observational data you could assume, and sometimes some of the edges might be missing in some of the graphs. So it's true, we're not doing intervention design. So the task is we also do this in causal discovery. Somebody has given us like a pile of experiments, and we try to find the graph from the pile of experiments. We're not deciding actions, that's true. We're not doing that. It's more like a passive version. But it doesn't mean, so the person could have done the action. So it doesn't mean that so we're kind of agnostic about whether it's intervention or not. So the graph can change in the different types of distributions. So is
it the case that you're really somehow trying to exploit the context specific independence in this now particular case? Is that because that you're targeting
case, so actually that's a good point. We do in a sense in this specific case because of the assumptions that we have some kind of context specific independence. But in general, in the joint causal inference paper, they're not context specific at all. We find dependencies across that kind of span across the different domains, but they're not context specific. So they're not given this context, like in this context, this is an independence. We try to kind of formalize it together.
But if you're saying that some edges might be missing in some domains, that feels like a context-specific independence, right? Like
yeah.
In this particular domain, these edges are not present.
So what I meant is in terms of, let's say, okay, let me go to the joint causal inference part. There's no space. Yeah. So let's assume we do have in one domain we have x causes y, and in the other domain we have x and y are independent. If I take them together, I will get x causes y, and there is a domain here that changes the way that x and y are interacting. But so usually if you have like different graphs in different domains, when you put them together, you get the union of the graphs.
Yeah. And
this would be maybe better explained in the structural causal model in a sense, because in the structural causal model example I gave, sorry about this here. So in this case, x2 is not depending, x2 here is not depending on y in this domain, but if you take the graph together or the structural causal model together, there is an edge. So this could easily represent the perfect intervention of x2. It could easily be that you have This is observational data. Here you did a perfect intervention on X2, now X2 is fixed to 1. So they can be also interventional data. Even if you don't do the interventions, you can still use interventional data. Does it make sense?
Yeah, I suppose so. I mean, just the
Sorry,
additional.
I'm not sure it's helping what I'm saying. I'm hoping it's, at some point we will converge.
Perhaps we should take it offline. But
By the way, Joris is going to say something because I'm sure you have ideas on this as well.
Oh, I think many questions were asked and many answers were given. Is there anything specific that's still unanswered?
yeah, so
I think it's really the way we talk about interventions and observations. It's honestly, it's not just confusing to you. It's been a bit confusing also to some of our reviewers. That's why, if you notice, the ICAI paper, which we use in the paper of 2018, is actually from 2021, because it took some time and some convincing that things can be seen mathematically as interventional. It doesn't really matter. A soft intervention doesn't really matter. In this domain, if you don't know the targets and it's soft specifically, it doesn't give you much more information than just a different graph.
So yeah. So my question is, which we can take it offline, but my question is, how is the problem different from learning a Bayesian network?
A Bayesian network is on a single distribution usually, right?
Where we have additional C1 up to whatever C variables. With somehow, some prior knowledge that the C1s are not affected in this way.
So essentially, the contribution of our joint causal inference paper is that you can get things that people thought were different, like learning graphs over different distributions, with this simple trick, clearly very simple trick of the D or the context variables. It doesn't really matter. Then you can actually get it back to the situation you're saying.
I see. Okay.
So you are right. You're right that in the end that's what we do, but that's.
I see. So it is the formulation of the augmented model that is actually the contribution.
Yes, and not just the formulation. The formulation is simple. It's more like convincing people that the formulation is okay.
Yeah. Convincing reviewers is indeed.
Several pieces of measured theory, and stuff like that.
I think I got it. So. Cool. Thanks.
Yeah, I guess we really punctually close off the webinar now.
All right.
Thank you all for attending. Thank you, Sarah. Yeah, we hope to see you all at the next opportunity.